you for the introduction. My name is Sebastian Daberdaku. I am currently the data engineering tech lead of Cardo AI, a global structured finance-focused fintech whose technology has facilitated the efficient management of over $40 billion worth of assets, integrating and standardizing data from over 100 different sources. My expertise lies in building and managing data platform infrastructures with technologies such as TrinoDB, Apache Spark, Airflow, Databricks, and the related cloud architecture, mainly AWS with Terraform.
Hi, I'm Jan Was. I'm a software engineer at Starburst, and I'm one of the maintainers of the Trino Helm chart. The Trino, I'm going to talk briefly about how we're developing the Trino Helm chart. The Trino Helm chart can be found at this repository, this GitHub repository, and there's a very brief instruction here how to install it. You can add. We publish it to using GitHub Pages, so you can add this as a repository in Helm, and you can just install the chart, and you will receive all the updates. There is a if you open the same URL that you can add to Helm as a repository, you will see the documentation for the chart, and this is automatically generated from the values YAML file. So everything you see on this web page is also available as comments in the values YAML, the default one, including all the examples. Here are very short development guidelines that I personally try to follow when I'm reviewing pull requests in the Helm chart. So the most important thing is any kind of change or any kind of change that you're proposing in a pull request needs to work correctly. So the first thing I try to check is that if the CI workflow that runs for every pull request completed successfully, and then I check if the changes in the pull request are covered by the existing tests or they require new tests. It's also important to make everything as robust as possible. This means that we have to cover all edge cases, like think about in what ways users can use a feature in the chart, and to make sure that we cover the needs of different users. The last thing is that we need to make it easy to use. This means that we don't necessarily want to introduce more complexity over Trino. Trino has a lot of configuration, so we try to keep things simple, and again, just think about how users will interact with this, and so like things should be pretty obvious. A while ago we introduced a very simple test framework in the chart repository. This allows us to clear out the pull request queue because we can merge changes with confidence where we know that everything works, and which includes this even includes testing on different versions of Trino. For example, we added tests for versions of Trino that where each one requires a new version of the JDK. Just to make sure that the JVM flags are correct in the chart. This also allows, having a framework like this also allows you to test your changes locally, which is important for quick feedback and a very tight feedback loop. So you don't have to rely on running the tests in the pull request. You can always run them locally. The tests should work on any kind of Kubernetes cluster, but the test script provisions a Kubernetes cluster using kind, so it all runs on your laptop. And finally, the tests are run end-to-end, which just means that we deploy the chart on an actual Kubernetes cluster with a set of example values. So this should match exactly what you're doing on how you would use the chart in production. And lastly, I just want to talk about the existing test suites. You can see there's quite a few of them. So we constantly try to improve test coverage. Let me just quickly go through all of them. So the first one is the simplest one, which just installs the chart with all the default values. We do need to make sure that all the defaults are working correctly, so that the chart doesn't really require any configuration out of the box to be tested. The second one is deploying Trino as a single node. So it's gonna run one pod of Trino that's running both the coordinator and the worker. So it can actually run queries, but it's just a single Trino node. And the third one is our most complete test that gives us the best test coverage. So it just tries to exercise as many different options in the values YAML file as possible. All the other ones are like specialized versions of this, testing more advanced features. So we allow, the chart allows you to deploy multiple Trino clusters in a single namespace. So we test this. You can use different access control systems. You can configure an exchange manager to run Trino with in the fault tolerant execution mode. We have a test for Graceful shutdown, which Sebastian will be talking about in more details in a few minutes. And lastly, we have tests for resource groups, because you can configure resource groups using like static configuration or load them from a database. So we do have an integration test that installs some rules in a database, and we run Trino and see if everything's working correctly. So this is all from me, and now I'm going to hand it over to Sebastian, where he will talk more about his contributions to the Trino Helm chart. Thank you.
Thank you, Jan. So before jumping directly to the contributions, I'd like to give a quick view of what we have right now at Cardo AI as data infrastructure. We're using a lakehouse implementation based on Delta Lake, which is built on top of AWS S3, and we use AWS Glue as Metastore. We manage our data ingestion workflows with Apache Airflow pipelines powered by Spark or with Databricks. And we build our analytics on top of Delta Lake using TrinoDB. And then on top of TrinoDB, we either use Apache Superset or our own suite of software as a service tools that we offer to our clients. All these components you see here are managed with Terraform and Argo CD. The Airflow, Trino, Spark applications run on AWS EKS, so it's Amazon's managed Kubernetes service. And we use Terraform to manage S3 buckets, Glue databases, Databricks workspaces, Kubernetes clusters, and then we use Argo CD to manage the Kubernetes applications, basically. At Cardo AI, we are running Trino on AWS EKS as I managed, which is mainly used by our structured finance software as a service suite for running analytical queries on mostly pre-aggregated data. The queries are generally short-lived. What I mean with short-lived is most of them run in under 1 second. All right, so this is our target use case, let's say. And they're used in real time to populate our front-end applications. We initially deployed Trino in EKS using our own fork of the Helm chart, where several of the features that I'm going to present here were initially developed. But as you all know, Trino development is really fast-paced, and there were also new features coming up in the chart, which were really nice. And keeping up, merging the new features in my version of the chart was becoming a chore. So came to the conclusion it was best to then donate what was useful to the community maintained chart from the developments that we had done. So let's start with the first contribution. The first contribution to the Helm chart I'm talking about is making the default TPCH and TPC-DS catalogs optional. By default, the Helm chart will create these catalogs, providing a set of provide a set of schemas to support the corresponding database benchmarks with the same name. These connectors can be used to test capabilities, query, syntax of Trino without actually having to attach or access an external data source. And these are also very useful if you are fine-tuning the performance of your cluster. However, very useful, but once you're done with them, users might want to, disable them to remove clutter. And another interesting feature that is kind of hindered by the automatic creation of these catalogs is the possibility of using dynamic catalog creation. I believe it's an experimental feature still, but is a feature that allows you to create new catalogs or new instances of connectors with SQL commands without having to restart the Trino cluster. And so, as I mentioned, with this new development, these catalogs are still enabled by default for backwards compatibility, but can also be disabled if the user wishes to do so. As you can see here, just provide null for both of them or one of them, and then it's disabled, not mounted automatically by the config mount. Another feature implemented in the Helm chart is the templating support for the additional config files, which I believe is quite interesting. This configuration allows users to add custom configuration files to the default Trino configuration directory, both on the coordinator and the worker, or depending, either in one or the other or both. Now, with the change that I made, these configurations can be templated. As you can see in the second last row of the slide, there's the TPL function. And in this slide, you can see what I believe to be an interesting example where this feature can be useful. And that is when you manage the file group provider configuration. Now, the file group provider is what allows you to map users to groups and then use groups for access control in the access control rules. Trino requires the user to provide the user group assignment with a list of groups in a file, one per line, and separated by columns. So the group is separated from the users by a colon, and the users are separated from each other by a comma. The problem with this configuration is that it becomes difficult to manage when handling a large number of users and groups. So think of having tens of groups and hundreds of users in each of them. It becomes quite a mess. Now, it would be, it's much more convenient if the users and groups could be handled as YAML list and YAML objects. In the example that I'm showing here, we can manage groups as lists of users. As you can see, there's the admin list of users and the group one list of users. And here you have the possibility to use your editor to collapse the list you're not interested in, keep the list sorted, and it's much more easy to maintain, to check the history of the Git edits. When was a user added or when was a user removed from the list? It's much more, it becomes much easier to check a Git blame for these kind of changes. And also the resulting group provider file is, of course, in the right format. If I may go back 1 second to the previous slide, you can see here that I'm mounting two files in the additional config files configuration. One is the group provider properties, where I'm telling it to use the group provider.db file. And then in the group provider.db, I'm transforming the configuration provided down there in the correct format. So now to the worker graceful shutdown feature. The worker graceful shutdown is a really interesting feature that allows the Trino coordinator to understand or to know when a Trino worker is about to be turned off. And so it can basically stop sending it tasks and queries to perform. This is particularly important if you're scaling down, for instance, Trino workers, or if you're running Trino workers on spot instances, which, as we might know, are can be interrupted by the cloud provider, and this allows basically you to have queries that don't fail from the point of view of the user. So if a user is running a query and the worker for some reason is turned off and Graceful shutdown is being used, the user will simply see a slightly a query that's running slightly for longer instead of seeing a query that fails, basically, and having then to resend the query to the Trino cluster again for computation. Now, to enable, when we enable the feature in the Helm chart, it does a bunch of stuff, and simply because to enable it, it's possible to enable it manually, of course, but it requires several steps, and this is where the Helm chart actually simplifies stuff for the user. So it adds the pre-stop lifecycle event to all the worker pods, which this is the actual code that calls the shutdown API on the worker when the pod enters the when the pod receives the SIG term signal, configures the shutdown grace period property, configures the worker's access control. Now, the worker by the API by default does not allow users to call freely the shutdown endpoint. Access control must be configured, and the chart does this for you automatically. It also validates the worker termination grace period in seconds value, which, if you read the documentation, it must be at least twice the shutdown grace period. So if the user makes a mistake, the Helm chart will actually tell them that they have the wrong configuration. And finally, ensures that the worker lifecycle is not set because it would conflict with the pre-stop lifecycle event that's created automatically by the chart. I think one notable use case of the worker graceful shutdown is the one that we are currently using in Cardo AI, which is implementing what I call a cost-effective deployment of a Trino cluster. As I mentioned, we use AWS AKS, and we manage EC2 nodes of the Kubernetes cluster with Carpenter. If you don't know Carpenter, the main difference between it and the cluster autoscaler is that Carpenter provisions EC2 nodes directly, calling the AWS API, without resorting to node groups. So you don't have to create node groups beforehand as you would do with cluster autoscaler normally. And in the example that I'm showing here, I have an on-demand EC2 instance running the Trino coordinator, and then spot EC2 instances running the Trino workers. Now, what happens is that when a spot instance is about to be terminated by AWS, AWS actually tells us this with 2 minutes, two minutes beforehand. And this event is captured by an event bridge rule and sent to an SQS queue, which then Carpenter continuously pulls events from. And so Carpenter knows 2 minutes before a node is going down that this is going to happen, and so has the time to taint and drain the node and spin up a replacement one. By draining the node, since we have configured the pre-stop lifecycle hook, by enabling graceful shutdown, the worker will enter the graceful shutdown state, and the coordinator will know that he needs to stop sending tasks to this worker because it's about to be turned off. Another thing that can be added, enabled, is the fault-tolerant execution, to automatically retry failed queries. If in the grace period the query didn't have enough time to terminate, you can then fall back on the fault-tolerant execution, and this provides the users a seamless experience, so they don't see their query failing because EC2 nodes are being interrupted. they simply might see a query taking slightly longer. Okay, so that's it. Another I believe interesting application is when we want to scale down workers. So imagine we have a horizontal pod autoscaler, and here again the graceful shutdown mechanism will stop. Will be used so that the coordinator will stop sending queries and work to do to workers that are about to be scaled down. By the way, it's important, at least in my experience, to keep the coordinator in an on-demand instance so that it's never interrupted. If the coordinator is interrupted, the connections are lost, and it's at least for our applications, it didn't provide a good user experience. So, but it's a neat, balances out costs nicely. To test worker graceful shutdown, as Jan mentioned earlier, I wrote a test. This basically does two things. Use kube control container that tails one of the workers' logs and looks for the shutdown request message. And another kube control container deletes that same pod, triggering the pre-stop lifecycle hook. And this is an extract of the pod. You can see that I am looking in the first container args. I'm looking for the shutdown requested string, and the second container is just deleting the pod to trigger the graceful shutdown command. By the way, this also tests that the graceful shutdown access control rules have been correctly configured, because if they weren't, you wouldn't see the shutdown requested message. It would receive an unauthorized error on the logs. So it's more or less an end-to-end test, I believe. Another contribution that I made to the chart was enabling the JMX exporter on Trino worker nodes. JMX can be used to collect a large variety of metrics, including the ones shown here in the current slide. Now, some of these metrics are worth monitoring also on the worker nodes. Originally, the chart, before my contribution, it was exposing only the JMX metrics of the coordinator. And the feature that I developed, when enabled, will add the JMX export configuration, will add a sidecar to the container to the coordinator and worker nodes, and will enable Prometheus scraping by creating a service monitor CRD. For scraping the metrics from the worker nodes, a headless service, if I recall correctly, is created, which serves as a target to the corresponding service monitor. Now, to test this feature, there were already tests in place. I just expanded them to account for the metrics of the worker nodes. So to wrap it up, Prometheus is installed in a kind Kubernetes cluster. Trino is then installed with the JMX exporter feature enabled for both the coordinator and workers, and then we verify that the JMX metrics are actually being collected by Prometheus by calling Prometheus directly. Another interesting feature that was implemented was the network policy support. Now, Trino supports multiple authentication mechanisms, and all of them require secure connection using TLS and HTTPS or process forwarding enabled. So if you don't enable HTTPS, you cannot use authentication in Trino. So, and to configure authentication, there are basically two alternatives. One is to use a TLS terminated load balancer or proxy in front of Trino, which is also the preferred way according to the official documentation. The second one is to secure the Trino post directly with valid TLS certificate, which of course requires the user to manage certificates by themselves, make sure that when they're replaced, when they expire, if they are self-signed, they must be installed in every component. And ultimately, this will also result in an increased CPU utilization for the encryption, decryption, and these are all CPU cycles that don't go towards query processing, right? So in general, people would prefer the first of the two alternatives. Now, when the user decides to go with a TLS terminated load balancer or proxy solution, the Trino cluster would still be unprotected from unauthorized access from within the Kubernetes cluster. So from outside, we're okay, we're protected. What about if another pod in the same cluster tries to connect to Trino? Other pods could try to connect to Trino or to the Trino service or the Trino pods using the internal Kubernetes DNS name, right? And they would not be required to provide the password, and so they would be able to impersonate any user they wish. Just to make an example, if you have Apache superset deployed on the same Kubernetes cluster as Trino, a user could create a connection to Trino by guessing the DNS name of the service, which I guarantee you 99% of the time is going to be trino.trino.svc.cluster local at that port 8080, because who is going to change the port? And here is where network policies can be really helpful, because they can provide protection for unauthorized access from within the Kubernetes cluster itself. Specifically to this use case, they can be used to only allow ingress traffic to Trino pods from pods with certain labels or from given CIDR blocks. Now, to give you an example, this is more or less what my Trino deployment looks like in Cardo AI. I have the AKS nodes running on a private subnet, and then I have a TLS terminated application load balancer. Notice it's running in another subnet. This way, I can use the CIDR block of that intra subnet to so it can allow it to access the Trino pods. At the same time, I can block the connections from any other pod from any other namespace, and only allow connections to the Trino pods to themselves. So like coordinator can talk to, of course, to Trino workers. It can talk to the ALB, and this time, in this case, any other application has to go through the load balancer, which means that they'll have to provide valid authentication if they want to connect to Trino. To test network policy connection, I also wrote a test, the dedicated test. Here, the idea is that if the network policy is enabled, connections from unauthorized pods will time out because they won't be able to reach the Trino pods. And as you can see in the last line of the extracted test here that I'm showing you the slide, I'm looking for the timed out error of the curl command that's shown. Now, as a future development, this is in the works. I haven't opened the pull request yet, Jan, but expect it in the next few weeks. I plan to add the worker Kubernetes event-driven autoscaling support. Now the Helm chart supports like resource-based scaling, like CPU and memory-based scaling, but scaling based on CPU and memory utilization is not necessarily a good approach for Trino workers, since, as many of you may know, Trino will always try to use all the resources available on the node it runs on, and thus these metrics might not indicate resource exhaustion. On the other hand, the number of queued queries could be a better indicator of the cluster's utilization. If the number of queued queries increases, then this would be a better indicator that the cluster could use more workers rather than simply CPU and memory. And in the simple example that I'm showing here, I'm showing a scaled object CRD with a possible trigger based on the number of queued queries. This metric is exposed using the JMX export feature and is collected in Prometheus. Kubernetes event-driven autoscaler then can run the provided query, the one that you see here under query, on Prometheus and make the decision whether to scale the workers up or down. Another interesting thing is that Keda can also be used to scale the workers all the way down to 0 for further cost saving. So this could be another cost saving feature, in my opinion. That was it from regarding the Trino Helm chart features. I would like to thank you all for your attention. A big thank you to Jan for his support. It's been a very, very good learning experience for me. And also I'd like to thank you for the Trino Champion nomination that I received. So that's it. Hope you enjoyed the presentation.